Hello there, math fans. This is a video I've wanted to make for a long time. In 2011, 12, and 13, I taught an honors calculus course. I had the same same 60 students for an entire year. They would do the same thing as the rest of my courses, but I would have additional projects. And I, over those 3 years, experimented a little bit. And out of those, I had this problem. And this problem kind of took on a life of its own, and I'm happy to finally share it. So as you can see on the screen here, I have an Eggo waffle, which is really where the story starts. I phrased the story in terms of pancake cutting, but it was an Eggo waffle that started this whole weird endeavor. And I'm going to make a series of videos on this because it's kind of a long story. So ultimately, I was trying to come up with an example where they got to use this method called trig substitution when you're integrating. And every morning, I have 3 kids. These are this one's now about to go off to college, and then he's a senior in high school. There's my daughter, and there's my youngest eating a pancake. So we're very bad in our house at cooking food, but breakfast we can do sometimes. There's my maximum number of pancakes I ever made in one time. And these here are 3D pancakes. More on that later. Called I was going to look up how to pronounce it. I forgot. That's for another video. Able skivers. I'll pronounce it better in the next video. But the question was this. Every morning when they were really little, we had to cut it up, or they would choke. I mean, when they were little, I guess they would sometimes take a cold one when they were teething. But I didn't cut it up like a pie. I cut it up using straight lines. So every morning, because the mornings, only on the weekends did I make pancakes, but every morning we would cut with a knife this way, this way, this way, this way. And that made 9 smaller pieces so they wouldn't choke when they were little. We often did powdered sugar, which I'm sure is great, is very healthy. Sometimes syrup. But that morning I thought, okay, I'm doing all these questions where we're finding areas of circles. This gives 9 pieces. And so I started the project with a puzzle. And the puzzle was, is it possible? And I'm sure this question had been asked before. It was original to me. That morning as I was making this, I was like, is it possible for me to cut it so that all 9 pieces have the same area? So I'm going to say something about that, but I would encourage you to pause and think about it. But that's what started my pancake cutting. So I was like, I really would like to do a better job of cutting this up using 2 vertical lines, 2 horizontal lines. For now, let's assume they're not intersecting. I mean, they're not, they are parallel is what I meant to say. So 2 parallel vertical lines, 2 parallel horizontal lines, and you make these 9 shapes. Is it possible to cut it in a way so that all 9 regions have the same area? Okay, so I'm sort of pausing there. And then we actually are going to prove that that's not possible. And then I made a separate discussion about, okay, what if you just want to cut it in thirds? We're now going to leave the realm of what I did with my kids, and we want all 3 of these areas to be the same. Now that is possible, and that requires a bit of calculus. So I did that with integration. I'll probably do that in my second video. So those of you that hate trig sub, I'll show you a chance to use it. So I did that project, and in the 3rd year I was like, oh yeah, I remember these 3D pancakes that you can buy at this restaurant called the Old European Bakery in Pullman, Washington, where I was a grad student. And I said, well, what if you cut those in thirds? Where would you cut? And how does it relate to this? Is it closer to the middle or further away? And then I had a student in the honors class the last year write their senior thesis project on cutting hyperspheres. I'd never studied hyperspheres before. And the idea is to take the equation you use for circles and spheres in 2D and 3D and extend them to whatever we mean by higher dimensions and define volume the same way. whatever we mean by volume in higher dimensions, but defined in the same way you would do in 2D and 3D. And then we asked, where would you cut them with a hyperplane? Boy, can you think of anything? Those people that aren't math people are listening to this and they're like, hyperspheres, what is wrong with you? But I want to pull it back, and we will start with this first thing, which is cutting it up. Now, at the time when I did this, and I'm going to do this on the fly. We're going to try to prove this on the fly. I didn't think about it ahead of time because I thought that would be more fun to challenge. Not fun for the viewer. But I found my solutions at the time. And over the years, I think I've realized, and this is from a piece of paper. Those of you that are my students may not have seen a piece of paper except on the final exam. But anyways, what I did at the time, the very first time I ever did this, is I figured out the total area of the pancake was 4 pi. I made the pancake radius 2. So I picked a particular number in the project itself. And I figured out, I said, here you go. I'd like you to cut it up. And I just did, I found, so that meant that the area of each one, we were hoping, would be 4 pi over 9. And my logic, and like I said, this is not, I think there's a much better solution to this. I'm going to try to derive it after I do this piece. And then I'll stop this video, and in a future video, I'll talk about some of the other questions. Okay, so what I did was I said, well, if this middle piece is a perfect square, and I labeled it. I labeled this distance A. I was trying to make it nice. Now, well, I guess I didn't argue at the time. Why does it have to be a perfect square? But I'm gonna, just for this, I'm gonna be a little less precise than a mathematician should be. We could say, well, how do I know that things need to be symmetric? I'm gonna rely on our intuition that in order for this solution to work, it would have to be symmetric. But I think that's a different thing. So I'll leave that to the viewer to try to convince themselves. But let's assume everything is symmetric. Okay, for this piece, since I didn't prepare properly. So I labeled these A, and then I said, well, I now can figure out what this is. I can figure out that the area of that square, I mean, I could have labeled it X and said X squared needs to be 4 pi over 9, and then take the square root. So sorry for you, the people that aren't math people. I'm sure you still like pancakes. But you could find that length, and then based off of that length, you can find essentially everything else. So I had the students, this is sort of a calculus approach. I had them integrate and find it and prove that the area of the other ones, if you choose that to be this length, then you can prove that these other areas are not equal to 4 pi over 9. That's kind of a bland proof. And I remember the students having all sorts of proofs. And so let's see if we can do, and maybe you have a better one. I'm intentionally not trying to give a best proof. Maybe you can email me one, and I'll make a video of the emails I got of the best proofs for my students. If you're not one of my students, don't email me. I have too many emails. Okay, so here we go. I feel like I had some students that just said, let's call this X and X and X. And I think they made that same assumption. And they made an assumption about the other pieces. So let's call this piece type 1. This is another piece type 1. This is another piece type 1. And this is really the problem, is you have these 9 pieces, but 4 of them are identical. And these 4 are identical. And you can almost do a continuity argument, which is, in order to make 1 and 2 the same, as you squish it down, you're going to have to mess up the one in the middle, this third one. And so let's go a little further until I get completely stuck in my logic here, and I'll leave the viewer to think about this. But you can say that the area of 3 is X squared, assuming symmetry. Now, I encourage someone to find a more elegant proof. This is what we try to do in math, is find a proof that is a proof from Paul Eredish, who I'll talk about in other videos. Talked about proofs from the book, that God had this book of the best most simple, elegant proofs. So maybe you can find the book proof. I don't think I have it. I have one of the world's ugliest proofs over here. And I had many students present nice proofs, but I don't think I still have any of that work. So this can be a new problem for you. But anyways, this has to be, if we believe this, and these other ones just can't match. So if this length, I think you could make an argument just without actually doing any calculation that if this is 4 pi over 9, then these lengths have to be too short. This is not possible. So I'll think about that. Maybe I'll make a supplemental video. I just wanted to get this series started. In the next piece of this video, I will go through and talk about the calculus questions. So for people that want to know about trig sub, that's the story. And for you, go ahead and try to find an elegant proof that this is not possible to cut up a pancake this way, which made me sad. I couldn't cut it up in a way. Every time I made these corners big, it made the other side small. I encourage you to try to cut up an Eggo that way. My pancakes weren't perfectly circular, but will give me that. Okay, thanks for listening. And in the next piece of this, I will talk about cutting up precisely into thirds, and that'll be more math. And then I'll talk about cutting up spheres. I'll talk about the project. And there's more. There's a lot more questions about cutting up areas. But for now, I just have a couple more videos planned, 2 or 3 more. All right, thanks.